Good morning. Let's start. In the previous lecture, we have considered the so-called change basis problem and start to study the change coordinate system problem. Now we will continue to study this problem, and we start to study the conic section. It will be first part of the SEM. I recall that main definition in the previous lecture. Let S will be first coordinate system, namely the origin O and the base. We will denote the base by letter E. Is all coordinate system. And we have, and we have the new coordinate system, the new origin O prime, and new base U. New coordinate system. And we have also the coordinate. The coordinate of the point O prime is given, and let this coordinate A10, A20, and AN0. It means exactly that the coordinate of the vector O prime is equal these values. Other words, the vector O prime can be present as a linear combination of the basis vectors with coefficients, with these coefficients A10, A20, and so on. In other words, we have the following equality. And we have also the relation between new bases and old bases. Namely, we have the first, we have the following equality. U1 is equal C11 E1 plus Cn1 E1, and so on. Cn is equal Cn1 E1, and so on, Cnn En. And we also introduce the matrix C, which is equal this matrix is called the transition matrix, and we also denote this matrix by SP E to U, the matrix transition from the old basis to the new basis. We also use the following to form the recording of these equalities. First of all, the short notation UI is equal C the short notation for the previous equality. The system of equation 1 is equivalent this short recording of this equation 1 prime. And we also use the matrix notation, namely let U be the new basis, U1, UN, E the old basis, U1, UN. And we can consider the following matrix equality, namely U1, UN times C is equal U1, UN, or E times C is equal U. The shortest form for the recording this relation between new and old basis. Let's consider the following draw. Let example. We have the old coordinate system S and the new coordinate system S prime and O prime, and let M be the arbitrary point in the plane. In our case, M be arbitrary point and let its coordinates x1, xn be the coordinate in the old coordinate system. Coordinate of the arbitrary point in the coordinate system S. And it means that the coordinate of the vector OM is equal these numbers, namely vectors OM can be decomposed as and present as a linear combination of the vectors of the old basis E, namely xi, ei. And let the coordinate of the point M x1 tilde xn tilde be the coordinate of the M in the new coordinate system. We will use the following notation. M s prime is equal x tilde 1 x tilde n transpose. And we also use the notation ms. Let's continue. See the square bracket for this notation. And our claim to express the coordinates of the point M in the old coordinate system in the terms of the new coordinate system. Our claim to relate these two vectors one another. And we have the same relation between new basis and old basis, and we can rewrite this relation in the matrix form. And easy to see that coordinate of the point M in the new coordinate system are the coordinate of the vector O prime M in the new basis U1 and U2. And coordinate of the point M in the old coordinate system is equal to the coordinate of the vector OM in the old basis. And let's write this relation in the vector form. Coordinate of the vector OM in the old basis. The coordinate of these vectors is equal x1, xn. Namely, it means that vector OM is equal to the following linear combination xi, ei. And O prime M, the vector O prime M is equal to the following linear combination of the vector of a new basis x tilde I u x tilde j uj. And we have the following equality: O M is equal O prime plus O prime M. And we have also the third equality: O prime is equal AI0 VI. We have the three following three equality. And let's substitute in this vector equality these three equality. And after this substitution, we obtain the following equalities. OM is equal X I EI is equal, substitute have the following three substitution. OM is equal the following linear combination. OO prime is equal I0 I EI plus O prime M is equal the following linear combination. X tilde J J. And we have also relation between new bases and old bases. And let's substitute this equality in this one, to this one. After this substitution, we obtain the following equality. You can simplify the last expression, and we can change the order of summation, and after that we obtain the following equality. First of summand, we also rewrite. Rewrite, and we obtain and the second summand, we change the order of summation. The first sum. Yeah. Oh. The question? Thank you. Excuse me. 0, 1. What do you mean? I don't understand your question, but I simply repeat the explanation. We have two coordinate system. This example, the example of the plane, the medical plane. In this case, we have basis which contains only two vectors, E1, E2, U1, U2. And we have two coordinate system. Old coordinate system as and new coordinate system S prime. And we have the following datum.
Excuse me.
Yes.
Yeah. My question is, well, for example, AI0, okay? Why don't we just write it AI?
Yes. This this means the coordinates of the point O prime in the old basis, namely O prime in the old coordinate system. These coordinates are equal R10, Rn0. It means that the coordinates of the vectors of the vector O prime are equal these numbers, namely the vectors O prime can be decomposed as a linear combination of the vectors of the old basis with coefficients A0I, EI. These numbers are coordinates of the point O prime, a new origin, in the old basis.
And is there any case that we have, for example, A11 or A112?
In our example, these numbers, the coordinates of the vector O prime is equal A10 E1 plus A20 E2. The coordinates of the new origin in the old basis, etc.
Thank you very much.
Okay. And after this substitution and changing of the order of summation, we obtain the following equality. I'm sorry.
Sorry, Professor.
Okay.
How did we do the last substitution? I didn't get it.
We substitute this equation, and after them we change the order summation. This summation by I and this summation by J. We change the order.
Okay.
If we have the following numbers, D11, D1n, Dn1, Dnn. We have this matrix, and we can use the form summation. So, first of all, we can adding the values in the rows, and after them summon these values, the sum of rows. And first summation to sum, first of all consider the sum in the column, and after them we can consider sum of this column. And these two ways are equal, and we use this simple observation in our case. And after this changing order of summation, we obtain this equality. Oh, I'm sorry. I'm sorry. I'm sorry. UI. let's change uj, and I change in this excuse me, it's mistake. Uj is equal ei, and so, we summarize by the index I, and ij, and j is equal im, and in this formula we also ij, j. That's right. And ij, the up index I, and down index j, xj. Xj. And the vector is index ei. And after these substitutions, we obtain the following, the last equality. We can compare this part and this part. And we obtain the following last equality. We have two linear combination of the basis vectors. The any vectors have unique decomposition by the basis vectors, and from equality of this two decomposition, we can conclude that coefficients of these two vectors are equal. Namely, xi is equal this sum. We can use the one of the property of the vector operation, and the last expression we can rewrite in the following form. And we obtain the equality of the corresponding coefficients in this expression and in this expression. Namely, we obtain the following last formula. Xi is equal this formula is a relation between the coordinates of the point, an arbitrary point M in the old coordinate system, and the coordinate of this point in the new coordinate system. Namely, we obtain the following quality. We have the arbitrary point M, x1, xn be the coordinate of this point in the old coordinate system. This equality is equal product of the coordinate of the point M in the new coordinate system. These coefficients are from the matrix, the transition matrix, from the old to the new basis, and plus the coordinate point O prime in the old coordinate system. This is a matrix form of the previous equality. We can rewrite this equality in this matrix form. x1, xn is equal. Oh, I'm sorry. This form. This right order multiplication. This matrix form. So we obtain this claim, is our claim, this relation between coordinates of the arbitrary point M in the old coordinate system and in the new. And we obtain this relation in this following form. Example, in the case of the plane, we obtain the following formulas in the plane. Example. N is equal to, and in this case, we have the old basis E, E1, E2, and new basis U, U1, U2, and coordinate O prime we have also the S, the old coordinate system, OE and S prime, a new coordinate system, O prime U. And O prime has the following coordinate A01, A02 in the old coordinate system. It means that coordinate of the vectors of the vector OO prime R1, 0, R2, 0. It means that this vector is equal to the following linear combination and transition matrix C O P E U is equal C11, C12, C21, C22. And we have the following equality U1 is equal and in the matrix form this equality we can rewrite in this matrix form. Do you understand this? This notation. Okay. And in this case, this formula can be written in the following form. Let's M be an arbitrary point M, and with coordinate in the old coordinate system be x1, x2, and in the new coordinate system S prime, these coordinates are equal x tilde 1, x tilde 2. And we have the following relation between this coordinate. x1 is equal c1 1 x tilde 1 plus x tilde 2 plus in the case of the plane, we obtain the following enough simple formulas which related the coordinate in the old coordinate system to the coordinates of the point in the new coordinate system. The following formulas. And in the matrix form, this formula can be written in the following simple form. M S is equal P EU M S prime plus O S O S. The matrix form of these equalities. Any question maybe? That's all. We can consider some simple example of this relation. Maybe let's consider some simple example of the transition matrix. Example 1, example 2. Let's consider the case when two bases be orthonormal bases. It means that the vectors of these bases first orthogonal, and second, these vectors have a unit length. And we have such bases. First, old bases E1, E2, and let's all the region of the coordinate system. And we have also new bases. And let's O prime is equal O. The new basis was obtained by the rotation of the old basis on the angle phi. On the angle phi. This angle is equal phi. And easier to see that relation between new and old basis is following. U1 is equal the product of the sine, cosine phi on E1 plus sine phi E2. And U1 in our case is equal minus sine phi E1 plus cosine phi E2. We can rewrite this relation in terms of the matrix. In this case, the matrix C, the transition matrix from base E to U, is equal the following matrix. And this relation we can rewrite in this form: E1, E2, sine phi minus sine phi, sine phi cosine phi is equal U1, U2. Easy to see. If multiply this row on this column, we obtain exactly the first equation. And if we multiply these rows on first column, we exactly obtain the second equation. This product is equal U1, this product is equal U2. And we obtain exactly the system of linear equations. And this matrix equality is equivalent to this system of linear equations. Do you understand? Yeah. And in the matrix form, we can rewrite this matrix relation in the following form. This shortest notation for this relation. And in this case, we can rewrite the formula for the coordinates of the arbitrary point M in the old coordinate system S in this form MS prime. Easy to see, as the point O prime in our case coincides with O, the coordinates of the point O prime are equal 0. And in this case, we obtain enough simple formula. x1, x2 is equal cosine phi minus sine phi, cosine phi, x1 tilde, x2 tilde. And in this case, we obtain the following equality. x1 is equal cosine phi minus sine phi. This equivalent form to the relation between coordinates point M in the old and new coordinate system. In the case when matrix transition is a rotation matrix. Rotation matrix.
Sorry, Professor?
Yes.
Shouldn't it be minus sine phi x delta 1 for x1, the new coordinate system?
In this?
Yes, x1.
No,
x2, x1, x2, x1, x2.
Oh, okay.
Yes.
Sorry, Professor.
We can. Yes, the question.
Yeah, sorry. What if we change also the coordinates? I mean, O not equal to O prime. The only difference is in the plus O prime, right?
Yes. In our case, O prime coincides with O. In this case, only in this case, only in this example.
Okay.
Only in this example. If we shifted the origin of the coordinate system, this formula will be changed in the following way. In this, we must to add the following summand, the following terms. In the arbitrary case, the formula has the following form. You can to add the coordinates of the point, the new origin point O prime in the old coordinate system. In our case, these numbers are equal 0. And in this case, are absent this term. In arbitrary case, the following. The formula which related coordinate in the coordinate system and the old coordinate system has the following form. In the case of the rotation and shift of origin. If the shift is absent, we obtain the most simple form. You can check this formula to compare with matrix form of this formula. And we can this formula are equivalent. Okay. And we finish the first part of our lecture, and we can start to study the so-called conics. The second part of our lecture. Part 2. Part 2. Conic section. What does mean conic section? What does mean conic section? Let's consider the following naive example. We have in the space two intersected straight lines, one of them L and other L prime. And let's rotate this prime and this. And in this case, we obtain a so-called cone. And let's consider some plane which intersect this cone. If the plane orthogonal straight line A, we obtain the section of this. The intersection of this plane and this cone, which is called section, in this case a circle. If we consider most slope of this plane, the intersection of the plane and the cone is some curve. Each curve is called ellipse. And if we consider a plane which parallel the straight line A, in the section we obtain the curve which is called parabola. And in the case when the plane intersect other part of the cone, we obtain the curve which contains two parts, and this curve is called hyperbola. Ellipse, parabola, hyperbola. We obtain three kinds of so-called conic section. But we start with other definition of this conic section. Definition. After at the end of our study, we show that this geometrical definition will be equivalent the definition which will be our start point of our study. Definition. The locus of a point which moves so that the ratio of its distance from a fixed point and fixed line is constant. Is called a conic section. Or conic. What does mean this definition? We have some point and some straight line A. And let's consider the locus of the following point. Point M, maybe some point which moves the following way, that the distance between this point. Let's denote by fixed point by F and straight line by A. And let's be distance between P, let's be moving point, and F be fixed point. A be the fixed straight line. And let be distance between P and F. Let D be this distance, and D prime be the distance between P and the straight line. And we consider the locus of moving point P such that the ratio D prime is equal constant. Let's consider this ratio by E. And this ratio is called eccentricity. And this ratio is constant. Eccentricity. And we'll consider three cases. First, E is equal 1. E less 1, E greater 1. And by definition, in the first case, we obtain parabola. In the second case, we obtain ellipse. And in the third case, we obtain hyperbola. And I will going to show that this basic definition is equivalent the geometrical naive definition. And we consider one by one, step by step, these following three cases. And we start with first case, parabola. Yes? Mm-hmm. Hyperbola. 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 But I will start from this definition. In our case, this conic are geometrical locus which define this condition. The condition is a ratio distances d prime. D, the distance from moving point to fixed point f, and d prime, the distance between moving point and fixed straight line. In the first case, this distances are equal, and in this case we will obtain the conic parabola. And let's consider the first case, parabola. Let's change the notation and let f prime a m distance d distance d prime and let's r be the base perpendicular from m to a, and let's I'm sorry, this point P, and let the point and consider the perpendicular which pass from the f prime and intersect our fixed straight line L in the point K, and we have also a moving point P, and let's R be point intersection of the perpendicular which pass through P and intersect our straight line in the point R. And K is the same point, but this point is intersection of the straight line which pass from phi prime and intersect our straight line in the point K. And let also A and also A be the point intersection and let point A be the middle of the segment f prime K, is the middle. And by definition, this point belongs to our conic. And Okay, let's consider also the point A prime such that the distance between the distance between A prime F prime is equal F prime K. And by definition, this point I'm sorry. Yeah, that's all, enough. Let's calculate this distance and, sorry. I need let this distance distance is equal and let's consider the middle of the segment Fi, and let's all be the sorry. Let's O let's consider the coordinate system such that the line x coincide with our straight line, which pass from the point F and F prime, and let I'm sorry. Maybe more convenient. To change K and K prime. Maybe F this point, A this point, A this point, R this, K this. And let's consider this distance P divided 2 and this distance P divided 2. And let's consider the coordinate system such that x line coincide with straight line which pass from F and A, and y axis be orthogonal this straight line, and R be the base of perpendicular which pass from P to the our fixed straight line P. And let's D be the distance between PF is equal D, and PR is equal D prime, which by definition is equal D, which two distances are equal. Let's consider.
Excuse me.
Yes, yes.
Sorry. What is P over 2? I think RP is less than KF to write P over 2 in the middle.
Yes.
I don't understand why you wrote P over 2.
A is the middle of the segment K and F. K is the point of intersection, the straight line which pass from F and orthogonal the orthogonal to our straight line A. We have, first of all, we have fixed point F and fixed straight line A. Also, we have perpendicular which pass from F and orthogonal to A. And intersection of this perpendicular with our fixed straight line is the point K. And we have K, F, and straight line A. A in the middle of the segment KF.
Yes.
A in the middle. P be the moving point. The locus of this moving point is our conic. And R be the base of perpendicular which pass from the point P, the orthogonal to our straight line A.
Okay.
And after them, we define the coordinate system the following way. The x of abscissa OX is coincide with the first straight line which pass from K and F, and y-axis pass from the A, and A coincide with origin of this coordinate system. A is origin. And using this coordinate system, we obtain the equation for our conic. We will use the definition. By definition, D and D prime are equal. Let's coincide. Let P has coordinate x, y. And let's, using this coordinate, calculate the distance between P and R. This distance is equal. This distance, by definition, A is equal O, origin. And OK is equal OA, by definition is equal P divided 2. And by definition, OF is equal RF is equal P2. These two segments, the lengths of these two segments are equal P divided 2. And using this definition, we can calculate the distance D prime. d prime is equal x plus p divided 2.
Excuse me.
And,
in the first line, you wanted to write OK is equal to KA, right?
Yes, K, the point
No.
which lies
In the
on
first
the
line
our
you
fixed
wrote-
straight line. Yes, the intersection of the perpendicular which passes from F to the straight line and the straight line. K is a point of intersection. And this distance, by definition, the P is some parameter. And I define this distance as some parameter P divided 2.
Sorry, Professor, where is A?
This definition.
A.
K.
A, where is A?
A is the middle of this segment.
Oh, okay.
And A is equal the origin. No, A, let's first of all be the some point O, and O be the origin of our new coordinate system. Yeah.
So, Professor, yeah.
Oh, okay, I'm sorry. Oh, blah, blah, blah. I'm sorry. And let's absent only O. And let's calculate the distance d. Easy to see that d is equal x square plus y square. Oh, I'm sorry. I'm sorry. The distance between, I'm sorry. PF, I'm sorry, PFD. D is equal x minus, in this picture, the difference p divided 2 minus x, the point lies in the other place. We obtain the difference between x and p divided 2 plus y square. O F, oh my God. X and this segment x minus p1 and this segment is equal y. And this distance by Pythagorean theorem is equal x minus p divided 2 square plus y square. And this distance is equal x plus p divided 2 is equal x minus and we can consider the squares of the left hand and the right hand. And after the simple calculation, we obtain the following equalities, the following equality. And after simplification, after the following simplification, we obtain the following equality: y square is equal to px, and we obtain the equation which defines the parabola. The following equation. And in the picture, we can draw the following O, X, Y, L. They obtain the following picture. If we change this axis, we obtain the following picture. If we denote the ratio 1 and 2p by a, we obtain the usual parabola. Oh, I have no time, and next lecture we continue to study the conics. Thank you for your attention.